The mathematical relation between temperature and kinetics can be seen in the so-called Arrhenius equation. So Arrhenius equation as such, where k, or the rate constant, is equal to a, which is a pre-exponential factor that is characteristic to a certain reaction, multiplied by e power to the minus ea divided by RT. We have discussed that EA is the activation energy, or the threshold energy that needs to be overcome by a reaction to occur. R, as usual, is an ideal gas constant, and T, also as usual, is temperature in Kelvin. In general, the higher the temperature is, the bigger the rate constant, meaning that at higher temperature, in general, reaction will occur. Now, other factors that could also increase the rate of the reaction would be increasing temperature that we have just discussed, increasing temperature. Also, higher surface area for reaction. And also, addition of what we call of a catalyst. Now, catalyst is something that is involved in reaction, so it also reacts. However, it will not be consumed by a reaction. So in the beginning, you have the catalyst. By the end of the reaction, you will also regain or reobtain the catalyst back because it will not be consumed by that reaction. Although it will actively involved in a reaction in the sense that it will also collide with the reactants to produce the products. Catalyst can also increase the rate of the reaction. And in the molecular level, this can be explained if we take a look again at the energy plot, where we have the reactant over here, and say we have exothermic reaction, so the product is over there, like that. We know that there is a certain energy jump that it needs to overcome first, and this energy jump is what we call the EA, or the energy of activation. So this particular value from the beginning of the hill towards the peak of the hill, that is the EA. Now, if we have a catalyst, the catalyst will provide alternative routes. So this is the keyword, alternative routes, so that instead of climbing this hill, it will go to a different route, say the one in the color of purple. So it still go from the reactant side to the product side, but now instead of the high EA, we have two smaller EA like this that I have colored in green. And in this case, it is okay to jump the hill twice like this. But still, because the first hill is not as steep, it can jump more easily. And then the second hill is even less steep, so it can also jump more easily. And this purple alternative routes will allow the reaction to go faster. Because as we can see from the Arrhenius equation, the EA, if we change the EA to become way lower, and you see this is negative, the K will become larger. EA can only be changed if we find a different route of the reaction, and that exactly is what the catalyst will provide to a reaction. If we revisit the Arrhenius equation again, so we have this Arrhenius equation, we can also taking the natural logarithm of both sides. So we have ln K equal to minus EA over RT divided by ln A. So in this case, we can plot ln K as the y-axis and 1 over T as the x-axis. And don't forget, this has to be in Kelvin. Yeah, never Celsius, always Kelvin. And we will obtain a line that looks like this, so it will go down. The intercept here will be ln A, so this one. And the slope here will be minus EA over RT. So actually, if we have a pair of data of K and T, we can find the value of ln K, put it here. We can find the value of 1 over T and put it there. And then we can use this as the X value and this is as the Y value. And then we can perform again, or we can have linear regression, just like what we had in the previous videos. And from here, we can calculate the A, which is the interception at the y-axis. And we can also calculate an EA of a reaction. We can also do this comparison between two temperatures. So say that we have T1 and then we change this into T2. We can determine the change of K1 into K2 by comparing two different conditions only. So again, we have ln K1 equal to minus EA over R, and then in this case 1 over T1 plus ln A, and the other one would be ln K2 equal to minus EA over R 1 over T2, yeah, plus ln A. And we can just simply subtract these two equations to eliminate ln A. The ln A will be exactly the same because we are talking about same reaction. Yeah. Same reaction using the same routes. So the A will exactly be the same. And EA will also be the same. So if we try to subtract this, so we will get ln K1 minus ln K2. And this one will be cancelled out. Ln A minus ln A will be 0. And this one will be minus EA over R. And this will be 1 T1 like this, plus EA over R, and this will be 1 over T2. And then we can further simplify this equation to become ln K1 divided by ln K2. Yeah, don't forget your math lessons. And this one will be, if we take out the EA over R, so we will get 1 over T2 minus 1 over T1. So this is the final equation that we can use. If we change the temperature from T1 to T2, we can then calculate the K2 if we know the K1 and vice versa.